Hi, good afternoon, and welcome to the ZP webinar on screen printed electrodes. So just to kind of say that at ZP, we're not going to hang around. I just want to quickly show you that I do actually have some technology in front of me. And so it won't be one of those kind of just talking webinars. I've got a couple of sets of screen printed electrodes here. I've also got a potentiostat in front of me, so I will be doing some real world testing using screen printed electrodes and generally talking about screen printed electrodes and generally talking about how they're such a good vehicle for commercialization. With that said, let me go back to the slides and just to say that there'll be a couple of slides and then we'll be diving essentially straight into it. So with that said, let me go forward. And just to sort of say that, yes, we are talking about the commercialization of electrochemical sensors. At ZP, we do like to support the translation of science from the laboratory into the real world, and I'll show you some sort of real examples of that kind of translation this afternoon or this morning as well. I'll only very quickly touch upon Zimmer and Peacock, only one slide. I will talk about the current situation that we see what we do see, and I'll sort of enlighten upon this is there's a lot of papers being produced, but there's not necessarily so much translation out of the laboratory. And this is sort of lack of translation out of the laboratory and into the real world is kind of called the valley of death. And I was talking about this just the other day in a meeting, and once upon a time I used to say that was, this valley of death between academia and commercialization has been kind of a 20-year problem. It's not even a 30-year-old problem. This is a 40-year-old problem, and it may be even, it goes back to the kind of the foundation of modern university structure. I'll talk about the technology stack that we have that I think that really helps actually in the commercialization or translation of research out of the laboratory. And as I say, I'll do some demos as well. So just very quickly, Zimmer Peacock, we're launched in 2014. I realize that we've been running 10 years and 4 months, certainly gone quickly. We are ISO 13485. ISO 13485 just means that it's a company that's kind of certified for doing medical research, and we're certified for the development and manufacture of specifically electrochemical biosensors. So we're fairly qualified, especially with that 10 years of history that we've got. I have some hardware in front of me. I have a sensor or potentiostat that I'll use this afternoon, and I also have a couple of different types of screen printed electrodes from Zimmer and Peacock as well. Like I say, this will be more showing and rather than just talking. The current situation that we see is that if you look at the kind of literature, especially around keywords like electrochemical biosensors, electrochemical sensors, electrochemical assays, there's a sort of certain formula to papers, and these papers will have a kind of title, so we can sort of check that box. They'll have an introduction, we can check that box. They may have a mechanism. This one's sort of organic chemistry type mechanism or electroorganic chemistry mechanism. So tick, check box, that's all good. We'll have an experimental section where people sort of list out what they do. We all know that sometimes the details are not quite there, but check that box. We'll have some, let's say, cyclovoltammetry in this particular case, check. We may have some cyclovoltammetry or some voltammetry versus signal. So we kind of basically got a calibration curve, check, and we may finish with a conclusion. So we can sort of check that. That's a typical template for a electrochemical paper in this in the particular world that ZP kind of operates in. And then we've also got this, that's not unique. That paper that I just covered was actually measuring capsaicin. This one's measuring glycerol. They both share a common theme that they're actually real world applications. The first one was measuring capsaicin in chilies. This one's measuring glycerol in wine. So they're real worlds, they're not fundamental papers, they're application papers. But the same formula, we've got introduction, abstract, title, obviously, materials and methods. Here they're using screen printed electrodes, the characterization of those electrodes at different concentrations and different pHs, and then a conclusion. So we can sort of tick, 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 but it's very much the same kind of checklist as the previous paper. Now, when I was first discussing these kind of slides, I was actually told that these kind of papers that I was kind of characterizing, There's actually 25,000 papers produced per annum like this. So the kind of journal, biosensors and bioelectronics, biosensors. Yeah, there's even I just sort of noticed another journal coming out recently in this kind of arenas, but there are tens of thousands of papers produced per annum. So if this carries on over the next 10 years, we're going to have 250,000 additional papers like this. But of course, governments are asking what's the impact? If we're funding this, is it translating into real products? And in fact, they can even term this. They term it the kind of valley of death, which I'll discuss in a minute. Now, both those papers actually follow the same theme, and the theme is that electrochemistry is a very good science for making low cost, easy to use, minimum sample prep biosensors. And so, I'm playing this kind of video at the moment, but this is a kind of, in fact, I've got the hardware here. This is a kind of classical glucose strip technology. So both those papers, they will have keywords in them like low cost, easy to use. Maybe they didn't use the term minimum sample prep, but that's inherent in some of these statements. And so this kind of technology of using electrochemistry to make rapid test, you don't have to argue this particular case. The argument has already been made. This is, a poster child, can I say, for electrochemistry. Now, I'll just do a quick demonstration, and don't worry if you've just joined. This has been recorded, and we'll be sending out a recording very shortly. But let me just change cameras for a second and just kind of use that particular application as a sort of demonstration. So what does this demonstrate to us? First of all, if we want to make an electrochemical technology, we should be able to make it in this kind of form factor. If we want to make biosensors, we should be able to make them in a sort of screen printed electrode format like this. What this demonstrates is that, this kind of electrochemistry can actually deal with, or rather this kind of science can actually deal with quite complicated samples, like blood. And that's really a kind of, and there we are, we've even got a rapid result. So it even demonstrates that we can get to results. I've got 101 milligrams per DL there. So if you're in the US, the units they often use in the US for blood glucose is milligrams per DL, 90 milligrams per DL. But of course, with a bit of food in me this afternoon, then I've come back at 101 milligrams per DL. But the reason I do that is because those two scientific papers, which I say are two, and there's something like another 25,000 of those per annum, are all heading towards this kind of form factor. So the argument about electrochemistry and then screen printed electrodes, that argument is already made, and I would also suggest is already won, that you can make low cost, easy to use, rapid sensors or sensing technologies using electrochemistry. Argument over. I mean, it's just, that technology's now been around for a kind of good 30 years. I did describe that we are getting all these papers that come out, and they all got title, abstract, introduction, materials and methods, results, conclusion, and there's 25,000 papers just like that every annum. But in fact, they're not translating into real world papers. And in fact, this has been termed this kind of valley of death, where you've got people doing their PhDs, their postdocs, their principal investigators, and they can, with the resources that are available in academia, they can sort of bring that to TRL3. When really in commercialization, TRL9 is the kind of, a really matured product is TRL9. Not necessarily every product that we ever touch is actually at TRL9, but that's the kind of, the highest state of readiness that we can discuss when it comes to technology. I'm sure you've heard of the TRL, so just out of interest, if you've not heard of technology readiness levels, this is a NASA concept where NASA can kind of rank the readiness of a technology. So rather than just saying it's been proven in the lab, they would say that was TRL3. If it was sort of manufacturable and being manufactured but not yet released, they may say that's TRL7, for example. But governments, US government, European governments, they're very keen on actually getting these products out of the lab effectively and into the real world. in the UK, for example, they're starting to say, what's the impact of your research? And it's not just, that you're in general doing societal goods. They really want to know, is this actually translating into products? Now, this, as I say, this valley of death, this gap where actually technology is falling down between academia and commercialization. This is not a 20-year problem. It's not even a 30-year-old problem. This is actually a 40-year-old problem. And I think this gap, in part, in my very small world of electrochemical assay development using screen printed electrodes and potentiostats, the gap exists in part because, in fact, sometimes, not all the time, but sometimes the instruments that we're using and the way we're doing the experiments, they look like lab experiments. Whereas I would very strongly argue that if we were using potentiostats and screen printed electrodes that would actually look like products, we would absolutely close the gap between what I do in the lab and what I can do in the real world. Now, obviously, I'm super biased, so I'll just sort of say that those are not just pictures. Obviously, I have a couple of I have the Sensei All potentiostat in front of me here. I have some of these screen printed electrodes here. I have some samples in front of me, and I will be doing a sort of demonstration on that super shortly. But what we're trying to do at Zimmer and Peacock is, and we've actually been doing this for probably, well, basically from the beginning, is actually say, okay, let's stop doing research on cables and glassy carbon electrodes and things that actually just hold us back in the lab, and let's actually close that gap between laboratory research and research that can be translated into commercialization or commercial setting by using, potentiostats and technologies that look like real world products. Now, I've got here a sensor to cloud demo. So this is basically a reminder to remind me now. I have in front of me an app. You'll see this in greater detail now, but what I'm going to do is there's this QR code here. I'm just going to scan that QR code off my phone, which has now put this app into what we call essentially the chilling mode. And I will just stop sharing, and I'll just do you a quick demonstration. So don't forget, this is essentially the second demo. The first demonstration that I did was actually just demonstrating why I think electrochemistry has been demonstrated to be a very translatable science just by looking at glucose strips. But now what I'll do is I'll go quite quickly. So I'll be clumsier and faster than I normally would like to be. But look at these ZP screen printed electrodes. Look at the way that we're actually presenting them. These are presented much more like a product. So you can appreciate that, somebody who's doing real world science outside of a laboratory setting can actually say, oh, okay, well, that looks much more product-like than I was otherwise expecting. So these are our kind of screen printed electrodes. I'll take a real world sample, which I'll do pretty quick, like that. I will grab a tube. I'd like to say nothing's really rehearsed. I'm just going to grab the bits and bobs that I have around here now. So I have a tube. I have a pipette. The reason what I'm going through is the workflow that somebody, now this is a potentiostat, so don't think that this is just doing, for example, the analysis of this sample. I'll actually talk about amperometry, open circuit potentiometry, impedance spectroscopy, linear sweep voltammetry, cyclovoltammetry, square wave voltammetry very shortly. But I just want to demo for you here. What do I like about electrochemistry? I like the fact that this is a real world sample. It's not transparent. It's not filtered. It's cloudy. It's actually quite viscous. And I'm just going to put that sample into there. But this is, like the blood that I did earlier on, electrochemistry can actually deal with it. What I'll now do is grab a clean pipette tip. Just grab that out of that little bag. And what I will do is just grab some buffer. And I will just do this. So I just need to do this. I could use a bigger pipette, but I'll just do this very quickly. Everything's going to be done in front of you. We're almost there. Right. I was hoping I was counting that correctly. I tried to do 9 of those, but I might have slightly miscounted. But what I want to show you now is that's essentially my sample prep. So I've done, you can see how quickly I could do that. Now I'm just going to shake this up just really quickly. So I've got a real world sample in a buffer. I've shaken it up. My sample's now prepared. I can load my sensor into there, which is easy enough to do. Just notice no cables, not even that horrible slotting, where you try to slot something into a potentiostat. I just, to close it, just click that up. I'm just going to make sure I give this a name. I'm going to give this a name because I want to find this data later on. So I'm just going to call this tab 202. Done. Right. Now what I'm going to do is I've mentioned it, but I'll say it again. What's good about electrochemistry is not only that sample prep was quite quick and easy, but also sometimes samples are actually, people don't want to give a lot of blood, for example. So, as in the drop of blood earlier on here, I'm just going to take a drop of this, put it onto the sensor, close that up, and then I will go continue. I tried to remember to do a 1 in 10 dilution, so I'll just make sure that I remember that. Start measurement. And now I'm looking at current appearing as a function of time. So what I'm actually doing is some cyclic voltammetry here. So it's going to run that really quickly. I say really quickly, and then I'll just show you. I'm going to share my screen back with you now, if I remember how to do it. Yeah. So I've got a result on my phone. This is the first thing that this potentiostat's very good at. This is a real, how do I say, a real potentiostat. But we've actually got it. We can program it in such a way that actually you don't have to give people peak height or cyclic voltammetry. You can actually give them a number. So I want to just share, and it's the wrong. In fact, yeah, that will do. But I just want to share this with you real quickly. It said something on my phone. It said about 2,500 Scoville heat units. And it also said upload complete. So upload complete means something. I'm just going to log into something called Julie. This is probably one of the world's, if only world's, potentiostat that's actually integrated with the cloud. So the technology stack, so screen printed electrodes, potentiostat that actually talks to the cloud. It all comes as a single package. I can go into demo here. I can click my demo here and go here. Now, most of you this afternoon are probably in the US, so you're in a slightly different time zone to me, but I can see here today's date and time. I can see the file name that I just gave it, and I can see the cyclic voltammetry that I actually just recorded. So I'll stop for a second and just kind of say this. I showed you a couple of papers at the beginning, and if you came in late, don't worry, you can watch the recording, but I showed you a couple of papers. One of them was talking about measuring the capsaicin in samples, and one of them was talking about measuring glycerol in wine. But I've literally just done the first paper, if I can describe that. But actually, I gave a real world experience. A real world experience means, if I was a food technologist, working at the Makili company making Tabasco sauce, for example, I'm not interested in cyclic voltammetry. What I actually want are real, in fact, are real results. So we were able to give a real result. That result is actually saved up in the cloud. That result is actually coming from the peak height. And you can see that, in fact, in this cloud system, what we have is we have the file name that I gave it. This is the time in London, UK at the moment. This is the date in London, UK. This is the operator who did it. This is the first site CV. This is the second CV. This is the process data. I can go in here. I can discover, we've got all sorts of tools. This is called a data pipe, and a data pipe, I think this is the only potentiostat in the world with a data pipe where the signal can come in and we can do processing on it, which is smoothing the data, rotating the data, cropping the data, making the data fit a formula. I've even got the dilution factor. You saw me take the one sample and try to dilute it with another 9 volumes. I've got all that in there. And because of all that programmed in there, I was able to go from peak height to Scoville heat units. And it's just that final step that is always essentially missing. The papers often finish with, and here's my signal versus concentration. But of course, if they took their calibration factors and actually put them into this particular technology stack, which anyone can buy, they would have actually come back with a final concentration, and then they would argue that in fact they didn't finish at TRL3. They could then argue that they were finishing at TRL4 or TRL5. So that was the demo. As I say, I'll send you a recording. You'll be able to watch that in a bit. I've got another two examples, so and I'll go fairly fast. So what you saw there was a real potentiostat, but because of the QR code, I made it actually do a single analyte, but I used the screen printed electrodes. In fact, I didn't use those circular ones. I actually did use these rectangular ones in that particular case. The circular ones are quite good though, because if somebody's trying to do a lot of functionalization, then the circular ones allow people to just pipette onto them quite nicely. We put a 50 microliter drop on there, but in order for the potentiostat to know what it was doing, we actually used the QR code. So I suppose I didn't really sort of spell that out so much, but my phone is actually in a Bluetooth connection with that potentiostat. You can't control this potentiostat through a laptop. In this modern age, we need to inspire people. You know, it's a smartphone enabled potentiostat. The potentiostat sent the data, and in fact, I'll describe that. So the smartphone told the potentiostat what to do. The smartphone, the smart device, gave the potentiostat gave the data back to the app. And in fact, we sent all the data, as you just saw, to the cloud. In fact, I can just show it just like that. We sent all the data to the cloud, and we actually processed it in the cloud and actually turned the peak height into a concentration and sent it back to the smartphone. So suddenly then, you know, I think even journals are actually looking for papers with higher impact these days. And so being able to say we developed this assay in the lab and actually then we sent it to, let's say, real farmers or real growers or clinicians, and they were able to use it, you know, in a small trial, that's more impactful than just, you know, we did it in the lab with synthetic samples. And this potentiostat actually allows that to happen. The app that I'm using is called Sense It All. It's matured, and it's actually on the Google Play Store. It's also on the Apple App Store, which is much harder to get things on the Apple App Store. You have to have quite a mature technology. And we can use these QR codes. I might to do things like amperometry, open circuit potentiometry, impedance spectroscopy, linear sweep voltammetry, cycle voltammetry, square wave voltammetry. In fact, what I might just do is just stop sharing for a second. Just go to just change cameras for 1 second, which is go here, just to show you some of the kind of more, let's say, laboratory assays. Well, yeah, square wave voltammetry is sort of a bit of a favorite, so if I can get it. So now I've got square wave voltammetry, and if I go here, and then I've got essentially all my settings that I can do for square wave voltammetry. I'll try and get one of the other ones. So cyclic voltammetry. Again, I've got all my settings, and I can change my settings. So I can it's just a potentiostat, but it's more than a potentiostat, because actually, because of this data pipe in the cloud, we can actually then turn it into something that appears much more like a real product. Again, the whole raison d'etre at Zimmer and Peacock is to help translate science out of the lab. And so we've ended up making a potentiostat that actually behaves like a product. Just the look and feel of it doesn't look like a scientific instrument. It looks like something some say it looks more like a sort of Apple type device. And now in order to prove what we're saying, you know, for example, we've done capsaicin, gingerol, pH, nitrate, antioxidative capacity, glucose, potassium. These are all electrochemical, obviously. Lead, caffeine, resin, ferrotoxins. We've done all sorts of different analytes, but it's just because electrochemistry is such a powerful science. You know, we've got amperometry, open circuit potentiometry, impedance spectroscopy, linear sweep voltammetry, cyclic voltammetry, square wave voltammetry, and they're all available on the instrument. So we make one of those measurements, we send the data to the cloud, it goes through the data pipe, and then we're able to get a concentration out and send that concentration essentially back to the phone. So I said that we do 3 demos this afternoon. So I've got a couple of QR codes there. So at the moment, I'm in cyclic voltammetry mode. I'm just going to scan one of these QR codes and just see what it brings me up. It's brought me up ginger. So what I'll do then is I'll just stop sharing for a second. I'm going to change my camera just really quickly. And so at the moment on my Sense It All app, which is in Bluetooth connection with this, it says gingerol. I'll just flip that out. It actually says ginger. I will grab an electrode. I will plug that in. I'm just going to look for a sample. I won't prepare the sample this time because, I did last time and it took a little while. But I've just found a sample. I'm just going to get the pipette. But I'm doing this just to demonstrate this is not, a one-trick potentiostat. No, this is a real potentiostat. So I've got my sample, got my pipette. Put my sample on there. I realize I want to just give this a name so I can find it. So I put a name in there. That will help me find it shortly. I will go continue. I just know that I've quite diluted this sample quite a bit. So I'm just going to choose the right dilution. Start measurement. And again, I can see this is time along here and this is current. So I'm running a cyclovoltammogram, but I can sort of see a cyclovoltammogram being essentially collected there. It's given me, now notice the way we deliver that data. We're delivering that data in different units this time, ppm. How many times in a paper do we actually so much deliver the concentration of the analyte of interest? We actually just deliver the current. And current, of course, doesn't mean anything to anyone. So we've delivered them here, the concentration of that analyte. I'm just going to share my screen just really quickly because I just want to kind of go back to this Julie system. And I'm just going to go to reports here. I'm just going to do a quick refresh. I should have something that jumps up and says ginger. There it is. We can go in here and have a quick look at it. I can see, I can see all the peaks for gingerol in this particular system. And again, we have measured the peak height and we have converted the peak height into ppm. Now, how did we do that? If we go into tools and go to properties and I go to second scan, I can see that we've rotated the data. We've told it to go and look for a peak height at a particular potential. We've told it to what formula to fit it to, and we told it how much dilution we did. And the fact that all of that is available to you without coding means that you can go from a voltammogram peak height to concentration really easily and actually turn that assay that was just otherwise just another voltammogram in another paper into something that's actually much more like a product. Now what I'm going to do is I'm just going to I've got another QR code here, so I'm just going to scan that just for a second. So I grab my phone, scan that QR code, yeah, and it's come back now, and now it says caffeine. So I will flip the sensors out. I will grab a sensor. Just notice how quickly I can put these electrodes in and out, and it's all just easy and clicks all shut. I've got a sample here. This is actually, look how, again, this is nothing clever about ZP, but look at that sample. I mean, how many analytical sciences could you give them a sample that looked like that and then analyze it? The first thing they'd want to do is filter it. But electrochemistry is a very, very robust analytical science. So I'm going to take, I'm just going to get a clean pipette. Sample, open up the sample, take out this sample, in, down it goes. I'm just going to give this a name so I can find it. So I'll give it the name, not ginger this time. I'll give it the name T. Do that. Go continue. I'm just going to hit start measurement. And now this is doing something slightly different this time. This is actually doing square wave voltammetry. So earlier on, I was doing a couple of voltammetry methods, and I realized I should stop sharing that for a second so you can actually see that in a bit clearer. But if I was to summarize what I've done so far, I scanned the QR code. I moved it into caffeine mode. I took a tea sample. I've pipetted 50 microliters of that tea sample onto that. I ran the assay. And again, I'm displaying the data in the way that a food technologist in that industry, not, first time I did a test to you today, it was Scoville heat units. Second time it was ppm. This time it's milligrams per gram. So we're obviously always using the units that are most familiar, to that particular industry. So I'm just gonna go here again, go up. So this back end sort of database comes with the technology as well. I'm just gonna do a quick refresh on this. There's T, and it really answers the question, where is my data? And the nice thing about this system is your data is actually up in the cloud. Look, it's a very different voltammogram this time, but you can see that we've really found, there's even an interference peak here. But the power of this system, the way we've done a baseline subtraction here and then picked up that peak really nicely, all of this is actually available in this. So we've got, if I come under properties, I can see that we've done a pre-processing where we've done a baseline subtraction. I even sent a link to the original inventors of this baseline subtraction the other day, a couple of scientists in Poland. They were quite pleased to see, somebody putting some use to it. So I will just go to here. So I've done essentially 3 demos. 2 of them were voltammetry, but they were different settings. The third one was actually the square wave voltammetry. But what I'm really demonstrating is so many papers are falling into this valley of death. So many actual people who do this kind of research really have an ambition to launch a company. What's holding them back is reliable screen printed electrodes. And actually, in my opinion, and it's super biased, is actually they're using instruments that look nothing and operate nothing like real world products. But of course, this caffeine assay that I showed you, we did this caffeine assay in about 2 weeks because obviously we have our electrodes, we have our potentiostat, and we do understand our platform quite well. But when somebody does understand their platform quite well, depending on the target, they can be much, much more rapid to releasing a technology into the hands of real people who can actually benefit from it. And that's really the whole point about impact and commercialization. So in summary, what I showed you today is really kind of, 10 years at Z, we've built a platform with the intention in the end of saying, okay, there's a problem we've got in society, which is lots of papers coming. They're all very practical with real world outcomes. They're not translating. Let's build a technology that looks like a real product. So you can both do square wave, impedance spectroscopy, amperometry, open circuit potentiometry, cyclic voltammetry, do that lab work. But by the way, there's a data pipe in there, which means that we can turn those raw signals into actual concentrations, for example. And I showed you Scoville heat units, parts per million, milligrams per gram. We're just using the units that market would expect. And so we were able to sort of show a platform really relying on the reliability of our screen printed electrodes. You notice I did no calibration at all. How do I get away with that? It's because we're actually making a reproducible, repeatable screen printed electrode. And it's the quality of many screen printed electrodes that's being used in R&D that's really holding people back. If you do have any questions regarding the Sensi All platform, screen printed electrodes from Zimmer and Peacock, then don't hesitate to reach out to us. Most of you have, and I know you have my email already, so you can reach out to me just personally. But if you have any questions, don't hesitate to reach out to us. Okay, cool. Well, I appreciate that. And I know time's your most valuable asset, so I do appreciate you giving me the time this afternoon. Okay, take care. Bye-bye.